Welcome to the first part of lecture 20 on graph theory. So, in this lecture we will prove that complete graph with 5 vertices is a non-planar graph, and also we will prove that K33, that is complete bipartite graph with 3 and 3 vertices is non-planar graph, and also we will talk about one characterization of planar graph. Let me start with a definition of phase degree. We know what is a phase in a graph. If f is any phase then the degree of f is the number of edges encountered in a walk around the boundary of the phase. Okay, so let me explain this using an example. Consider this graph. G, and we can see that it has three faces. This is one face, this is another face, second phase, and this is another phase F3. Now, the degree of this phase F1, the degree of F1 is equal to 4, because the number of edges encountered in a walk around the boundary of the face. So, this is if the walk starts here, then the walk visit these 4 edges and come back to this vertex again. So, that is why this phase F1 has degree 4, F2 has degree 4 because the walk starting here visit 4 edges and come back to the same vertex. So, the degree of F2 is also 4. Now, what is the degree of F3? If you start from here, start from this vertex, for example, start from this vertex and then consider this walk, you visit this edge and again come back to this vertex and come back to the starting point here. So, you see that the number of edges encountered in a walk around the boundary of this face, how many edges you encountered here, visit edge 1, 2, 3, 4, 5, 6, 7, 8. So, the degree of this phase 3 is equal to 8. This is how you compute the degree of a face. Now, this is the second handshaking theorem says that the sum of face degrees is equal to twice E. The first handshaking theorem is the sum of vertex degrees is equal to twice of E, and here it is the sum of face degrees, and you can see that this is true because here in this example you can see the sum of face degree is 12 and there are the sum of face degree is 16 and there are 8 edges in the graph. So, this is twice of E. Okay, now next we move to another lemma. Lemma 1. Let G be a connected planar simple graph with V vertices, V greater than equal to 3 vertices and E edges. Then this is true, the number of edges is less than equal to 3 V minus 6. Okay. Since this is a simple graph, so I can say that each face must have degree greater than equal to 3, because you see it's not a simple graph. So, such multiple edges are not allowed. So, if this is allowed, if multiple edges are allowed, then a face can have degree 2 also, but since it is a simple graph, one face will have at least, this is the smallest face, smallest degree face that is possible, a triangle. So, each face must have degree greater than or equal to 3. So, can we write that twice of E, which is equal to the sum of face degree, but I am replacing the face degree for every face by a smaller quantity 3. So, this quantity is greater than equal to 3 f. F is the number of faces, right, because of the fact that twice E is sum of face degrees, sum over all faces, and each of them I am replacing by 3 a smaller quantity, because the face degree could be greater than 3 also. That is why twice E is greater than or equal to 3 and the number of faces is f. So, 2E is greater than equal to 3f, which implies that f is less than equal to twice E by 3. Now, from Euler formula, what we know is that we know that V minus E plus F is equal to 2. Now, I replace F by a bigger quantity, twice E by 3. So, this one is larger than 2, and from here you can check that, well, V minus 2 is greater than or equal to E by 3, which implies that E is smaller than 3 V minus 6. So, this proves that if G is a connected planar simple graph, then the number of edges is bounded above by 3 V minus 6. It can't have more than this many edges. So, this will be helpful to prove the result. That K5 is non-planar. Okay. So, what is K5? K5 is a complete graph with 5 vertices. So, it has 5 vertices, V equal to 5 and E is equal to 10, right. So, E equal to 10, and what we have, the upper bound for E is 3 V minus 6, which is equal to 3 into 5 minus 6, this is 9, and we know that E, the number of edges must be less than or equal to 3 p minus 6, but this is not true. So, here the number of edges is more than 3 p minus 6. So, K5 is non-planar. Okay. Now, the other result, or say we are trying to prove that whether K33 is non-planar, whether that can be proved using this lemma. So, we consider the graph K33, and this is what the complete graph, complete bipartite graph, 3 vertices. Right. So, this has V equal to 6 vertices and the number of edges 9, right. So, 9, which is the number of edges, and we compute 3 V minus 6, which is equal to 3 into 6 minus 6, that is 12. So, this is less than. So, the condition of the lemma true. So, we can't use cannot use lemma 1. So, we cannot use lemma 1 to prove that K33 is non-planar. Okay. So, we talk about another dilemma. This K33, it is a bipartite graph, and then we know that a graph is bipartite if and only if it has no odd cycles. So, that fact we need to use. Let G be a connected planar simple graph with V vertices E edges and no triangles. Then the number of edges must be less than or equal to twice p minus 4. See, note that K33 is a bipartite graph, and a triangle is an odd cycle, right. So, a bipartite graph can't have odd cycle, because we know that a graph is bipartite if and only if it has no odd cycles. So, K33 can't have a cycle of length 3 which is triangle. So, using this result, result that using this fact that the graph K33 does not have any triangle, we get an improved bound for the number of edges. Okay, so, this proof for this one here, since G is simple and triangle free, G is triangle free. So, you do not have a face like this in the graph. So, every face, and it is simple also, right. So, you do not have a face like this also. So, the minimum face degree has to be 4. Since G is triangle free, each face, so this is not allowed in this graph, this is not there in this graph. So, the minimum face size is 4 or face degree. So, each face has degree greater than or equal to 4. Now, again the same thing, that twice E is the sum of faces, and then I am replacing every face by, this is the sum of face degree. So, this is a degree of Fi, and I am replacing each degree by a smaller quantity. So, 4, and there are f many faces. So, that is why twice E is greater than or equal to 4 f, which implies E by 2 is greater than or equal to f. Now, if I use Euler formula, what I get is that V minus E plus f is equal to 2. This is the Euler formula, and I put replace f by a bigger quantity E by 2. So, this is greater than or equal to 2, right. So, V minus 2 is greater than or equal to E by 2. which implies E is less than equal to twice p minus 4. Okay, now we can prove that using this lemma we can prove this result, that K33 is non-planar. Okay. So, we will prove this. Suppose K33 is planar. If K33 is planar, then K33 is triangle free because it is a bipartite graph. So, we can apply this lemma 2 now, and it is a simple connected graph. Suppose K33 is planar, then lemma 3 says that this should be true. Okay, let us see. So, K33 has V equal to 6, E equal to 9, and triangle free, right. So, it follows from lemma 3 that 9 is, so this E equal to 9, this is less than equal to twice V minus 4, which is equal to twice into 6, 2 into 6 minus 4, this is equal to 8. So, this shows that 9 is less than equal to 8. So, this contradiction shows that what we have assumed at the beginning, that K33 is a planar graph, that is not true, that K is, or K33 is non-planar. Okay, so, using these two lemmas, we have proved that K5 complete graph with 5 vertices is a non-planar graph, and using the other lemma we have proved that K33, which is simple connected and triangle free, this graph is also non-planar graph. So, next we talk about another characterization of planar graph. This is Kuratowski's theorem, (1930). Two graphs are homeomorphic if one can make one graph into the other by edge subdivision. Okay, so we know what is edge subdivision. So these two graphs are homeomorphic because I can get this graph subdividing an edge. So this graph and this graph, these two graphs are homeomorphic because I can get this graph from this graph by subdividing this edge, right. And this theorem says that a finite graph G is planar if and only if it has no subgraph that is homeomorphic to K5 or K33. Right. So, this is one characterization of planar graph. So, this theorem can be, I just illustrate, I am not going to prove this theorem. So, this theorem can be used to prove that this graph is non-planar. Okay. So, this will take some time to draw this graph. Now, for these two vertices, so this vertex is adjacent to this vertex and these two vertices are adjacent. These two vertices are adjacent and these two vertices are adjacent. Now, we will show that this graph is it is very clear now that this graph is homeomorphic to K5 because we can see that this is K5 . Now, you can see that you can get this graph from this graph by subdividing this edge, this edge, this edge and this edge. So, by subdividing this edge you will get these two edges or a path of length 2. By subdividing this edge you will get this path of length 2 and by subdividing this edge you will get a path of length 2 like this. So, since this graph G is homeomorphic to K5, that is why G is non-planar. This is my G here. So, G is non-planar. So, just we have illustrated this theorem, a finite graph G is planar if and only if it has no subgraph that is homeomorphic to K phi, but we can see that this graph you just take this as a subgraph of this graph itself. So, this graph G is homeomorphic to K phi. So, the graph G is non-planar. Okay, so, we talk about, so we have seen the formal proof for K5 and K33 to be non-planar graph, and also we have seen one characterization of non-planar graph. So, we will stop here. Thank you very much.